Hello, hi everyone, um, and thank you. Thank you, Marcella. Thank you, Arno, for the opportunity to this tutorial for uh, allowing me to give this survey on quantitative coding and complexity theory of continuous data. Um, So this is a tutorial, which means that most parts, particularly in the first half, will be uh, about known results, but maybe arguably from a new perspective. But starting with the second part of this tutorial, I will cover increasingly new and more recent material that has emerged in research and collaboration with my PhD student, Donghyun Lim, who is also co-author of our extended abstract in the proceedings. So thank you, Donghyun, for allowing me to include this uh, results in the presentation. So that's it, and without further ado, let me fire up the slides here. Okay, so here we are. Right. So yes, and this is recent and ongoing research that has benefited from many similar discussions and feedback, including with Professor Akitoshi Kawamura from Kyoto University, with Matthias Schröder from Birmingham University, and Theo Darmstadt, with Svetlana Selivanova, who is currently research professor here at KAIST, right? By the way, I'm um, Martin Ziegler, and I had been professor of mathematical logic for 5 years at TU Darmstadt in Germany, and since last 5 years, I've been professor of computer science at KAIST in the Republic of Korea. And final discussion are with my former PhD student, Florian Steinberg, who graduated in 2016. So what's motivation? The motivation of this research is the observation that computer science has changed computing tremendously over the past 30, 40 years. So what started out as a paradise for hackers, including myself, we would just turn on your computer and start coding, now has become a serious both economic and uh, academic endeavor. So instead of just starting to code, which was sufficient and reasonable for one or two person projects with limited number of contributors. Nowadays, software are huge endeavors, and making them succeed reliably, that's a very challenging task. And computer science has indeed developed the tools and methods that are nowadays state of the art, particularly for large scale projects. So instead of just starting to code, one usually, and one has to, first make a rigorous specification of the problem to be solved or of the problems to be solved, because such a big project is usually divided, modular approach into several separate sub-projects with clearly specified interfaces that are then pursued independently. After the specification or as part of the specification, there may be a computability investigation, because there's no point in specifying something that cannot be computed. For instance, like an automated software verifier, right? That's easy to specify, but impossible to achieve because it's not computable. And this dates back to the work of Turing, and of course tremendously expanded by Stephen Cole Cleany. After and only after having established computability, then one can start looking for efficiency questions, namely complexity. Complexity theory arguably started with the work of Juris Hartmanis, and one of the gems in this field, or several of the gems, are of course the works of Stephen Cook. And once one has thus devised and found a provably optimal algorithm, right, that's complexity theory, then one can move gradually towards implementation, look at suitable high-level programming languages, right? No assembly coding anymore these days. And there, of course, the question of semantics of such a high-level programming language arises, and the question related to the question of formal verification of such a program. And to both Dana Scott and Tony Hoare have made significant contributions. And then one starts only implementing these abstract data types and putting them together to finally obtain the library or code. But the point I'm trying to make here is that this is a state of the art thanks to computer science. In the discrete realm, when we talk about computations that process discrete data like integers or graphs or anything that can be encoded as a finite sequence of bits for input and output. But this is only a very limited perspective of the actual range of applications in computer science. In engineering, the data involved is usually not discrete. It is, for instance, like temperature distributions over space, or stress tensor fields, differential operators. So all of engineering mathematics, I would like to say, is not discrete, but is real in nature, real in some sense, real numbers, real functions, real operators. And there, computer science has been considerably lacking behind in providing this tools and foundations. And just one point to illustrate, even the mere definition of computational complexity for functions, that's essentially to the book of Kerry Kuhl from 1991, right? And the definition of computational complexity for operators, that only is as young as 2010. That's 10 years old, basically the PhD thesis of Akitoshi Kamamura. And that's just talking about the definitions, not even mentioning the results. So I'd like to emphasize here that there's still lots of work to do and to go on to achieve a similar level of rigorous foundation and of tools to allow for rigorous software development, also for processing real data, and even more so for other kinds of continuous structures beyond the classical spaces of continuous and differentiable functions. For instance, when we talk about L2 functions, right? So the Hilbert space of square integrable functions, which is of extreme importance, for instance, in the theory of partial differential equations, there we don't even know how to define computational complexity. What is a polynomial time computable L2 function is a question that we have recently asked here at KAIST, and we're trying to answer. So the things we're still looking for the definitions in this promising and rising field, and to quote Doran Zeilberger's opinion number 82, he says, a good lemma is worth 1,000 theorems, and I agree, but preceding lemma are definitions. A good definition is worth 1,000 lemmas. So let's first strive to find the right definitions. Let's find the definition of computational complexity on abstract spaces like the L2 Hilbert space. Let's find the definitions of computational complexity for functionals and for higher types beyond functionals. And this is the motivation to my present tutorial, to my present talk. So to recall, let's look at the coding theory of discrete objects, and this is kind of trivial because their encoding discrete objects is either obvious or uh, doesn't matter much from the polynomial time perspective. For instance, we may naturally encode a graph, a discrete object, via its adjacency matrix. So matrix which has the same number of rows and columns as the graph has vertices and contains zeros and ones at the entries corresponding to whether an edge is present or absent. And this can be immediately encoded as a finite sequence of bits. Different encoding is by listing all edges, that is pairs of vertices with their given numbers, or by providing a rotation map. This is something that rotation map is heavily used in logarithmic space complexity investigations. And the point I'm trying to make is from the standard perspective of complexity, polynomial time, they're all the same. One can convert back and forth between them in polynomial time. So we don't really, and usually even don't actually discuss such issues of coding discrete objects. Things may become a little more subtle when we talk about encoding, for instance, integers, where there may be two natural ways. One is the binary encoding, so a sequence of bits such that they are weighted sum, binary sum equals the integer under consideration. And the other is the unary encoding, a sequence of ones whose length coincides with the value we're interested in. And these are still computably equivalent. One can convert back and forth, but as soon as we address the question of computational complexity, there's a huge difference. They have exponentially different complexity with respect to the unary encoding. For instance, integer factorization is polynomial time computable, but purportedly not with respect to binary encoding. So here, this is pretty transparent, where you have kind of grown up with this distinction and are well aware of whether and when to use which of the two encodings. But as we proceed to more general and abstract generic spaces, it is crucial to be aware of this possible difference. And there, the things will turn out to be not that obvious at all already in the real case. So in the real case, there's a famous folklore observation that every computable function is continuous. And that is already indication that something new is happening here, because now suddenly topological conditions become relevant. Well, one may argue that the same topological condition of continuity is also present in discrete computation, but simply not visible, because in the discrete realm, every function is continuous. So one could say it's nothing new, but one could also say that only looking at computation from the continuous realms reveals new insights into the discrete case, that because things have been hidden there. A strengthening of this folklore theorem, qualitative computability, qualitative continuity, has been observed by Kerry Ko in his 1991 textbook, namely strengthening polynomial time computability, computability to polynomial time computability. He was able to conclude or strengthen the conclusion from qualitative continuity to having a polynomial modulus of continuity that is quantitatively. And this is the kind of spirit, this is the kind of results that we are looking for throughout this talk. Quantitative strengthening relations between computational complexity and quantitative metric properties like continuity. And this will serve as a guide to a coding theory of abstract compact metric spaces as generic objects. For that abstract spaces, the qualitative coding and computability theory that has been well known since at least 30 years. There have been many investigations and characterizations. Nowadays, we know how to encode, for instance, an arbitrary generic Banach space so that it becomes computably has computably reasonable properties. But already for the space of Sobolev or even just L2 functions, we don't even have the definition of polynomial time computability. But we need this before we even can start investigating the computational complexity of, let's say, partial differential equations, which naturally involve such functions. So this is the motivation that led to this research project, and that is the topic of the present talk. So to overview of the talk, we're going to recall 4 natural naive encodings for real numbers and see that already in this seemingly well-known case, things easily become very involved and subtle. Maybe the first encoding that comes to mind is the binary encoding, right? So a real number encoded as an infinite binary sequence, that is as an element of Cantor space. And observe that this is sometimes not unique for dyadic rationals. For rational numbers whose denominator is a power of 2, there are precisely 2 such binary encodings. For any other real number, there's only 1. Another natural maybe way of encoding real numbers is by their construction as Cauchy sequences of rational numbers, that is by a sequence of natural numbers as numerators and denominators alternatingly even and odd indices that approximate the real number up to error 2 to the minus n. So again, if we encode every single natural number, numerator, denominator, in binary as a finite binary string, then concatenating all these finite binary string gives rise to an infinite binary string that is again an element of Cantor space as encoding of a real number. And observe that here uniqueness is even less present, namely here every single real number has uncountably infinitely many such infinite binary sequences as codes. On the other hand, some codes are not codes of any real number at all. So that's something to keep in mind when we later generalize this to representation. Next, natural way of encoding real numbers by using dyadic rational encodings. That's popular in numerics, where the numerator corresponds to the mantissa. So here we fix the numerator to be 2 to the n, with n of course running, and we only encode the we only encode the numerator, and the denominator is fixed to 2 to the n. So this again gives rise to an infinite binary sequence that is an element of Cantor space as code. And finally, the signed digit representation looks maybe like the binary representation, but it adds the additional digit -1. This it further increases the non-uniqueness. So for instance, the number 1/2 has the binary expansion 0.1000000. It also has the binary expansion 0.01111111, but it also has the signed encoding -1, 1 point -1 -1 -1 -1. So here there are even more opportunities for non-uniqueness. And these all look more or less natural. Maybe the binary expansion looks like the most natural, and this is in fact the one that Alan Turing had in mind or suggested. Well, technically it was the decimal, but anyway, when he first defined computability of real numbers in his very paper where he introduced the Turing machine. But after this paper has went into print, he became aware that this is not a suitable encoding because it renders addition uncomputable. So he was forced to publish a correction immediately this successor article where he mended that error and instead used, for instance, the racial encoding. And indeed, this was and still is popular among constructive mathematicians and among real computability theory. Here, addition is computable, but when we look more closely from perspective of computational complexity, it turns out that here addition does not have a running time, a bounded running time that only depends on the output precision. We cannot measure things depending on the input precision because input length, as in classical complexity theory, because that's infinite. So instead, here we measure computational cost independence on the output precision. But here, for racial approximation of the addition, there is no such finite bound as has been demonstrated, or for instance, in Klaus Weyrauch textbook in chapter 7.2. Whereas for the dyadic representation, addition is not only computable, but it is computable in quadratic time in a sense. Namely, observe that here code of a real number is a sequence of binary codes of single natural numbers, where the nth natural number, the numerator of this denominator 2 to the n, and since the real number r is between 0 and 1, that means that an lies between 0 and 2 to the n. Therefore, it has roughly n bits. And since the code is an infinite binary sequence of all these n bits numbers, if with n increasing, that means in order to arrive at the precision 2 to the minus n approximation, one first has to skip over all previous precision approximation of with error 2 to the minus n minus 1, plus 1, 2 to the minus n plus 2, and so on. And each one has length n, so that the total number of bits to skip over here is 1 plus 2 plus 3 plus plus n, and that's n squared bits. So that this is really a quadratic number of bits that a Turing machine has to skip on its input tape in order to even access the precision it is interested in. So this is good enough for complexity, for polynomial time complexity investigations, but we cannot really perform subquadratic complexity investigations because merely reading the input is already dominating then the actual computation. So if we're interested in even faster computation in subquadratic time complexity, then the signed digit representation encoding is the encoding of our choice, because here turns out that addition is computable. It's even computable in linear time by a deterministic finite automata. So to summarize, there are at least 4 and very natural ways of encoding the reals in a unit interval, but they have very different computability and very different complexity properties. And if we, some of them may be surprising to naive, naive from a naive perspective. But now imagine that we replace the real unit interval with a much more abstract space, like a compact subset of L2 Hilbert space. Then it's not at all obvious which encoding to use for that space with respect to, let's say, polynomial or even linear time complexity investigations. And this is a topic of this tutorial. In the first part, we have just discussed 4 natural ways of encoding real numbers, and we will proceed to to recall quantitative notions of continuity in terms of a modulus. That's just basically a scholemization of qualitative continuity, epsilon delta continuity that you know. And we will recall basic spaces that Turing machines naturally operate on that don't require any coding considerations, Cantor space, Baire space. And then we discuss computing over more general spaces by means of encoding them as elements of Cantor space, as elements of Baire space. This is a Weyrauch theory of representations and of realizers. And we will recall Kreitz-Weyrauch's notion of admissibility as an important necessary criterion for any computability theoretically reasonable encodings, representation. Reasonable in the sense that these are the ones where the famous Kreitz-Weyrauch representation, the main theorem, holds, which characterizes continuous functions in terms of continuous realizers. But our goal is to refine that complexity theoretically, and an important step and an important guide to that goal is the real case where much more is already known. We will recall a quantitative strengthening of the main theorem for this real case due to Carey-Coe, and our own further strengthening from polynomial to linear time main theorem. But our goal is to have refined quantitative notions of admissibility and a quantitative version of the main theorem for more general compact metric spaces beyond the real unit interval, beyond the basic spaces of Cantor. So that's where we're heading. And let's just dive right in by recalling for your convenience what is quantitative continuity as captured in the motion of a modulus of continuity. So to this purpose, let us fix metric spaces, and the function between these spaces is said to have modulus of continuity mu if whenever the arguments x and x prime are sufficiently close, namely have distance less than 2 to the minus mu of n, then the values f of x and f of x prime have distance at most 2 to the minus n. Well, this is kind of a quantitative version of epsilon delta continuity, where mu is called the modulus. This is not to be confused with what sometimes in calculus people call a modulus. They call a modulus a function from the positive reals to the positive reals. Here, this is more like the computer science perspective, which also explains for this powers of 2. Right? This is kind of like binary encoding or bit length. Okay, so in a sense, deep functions that are sensitive, where the value depends sensitively on the argument x, these are the functions that have large modulus of continuity. And as qualitative continuity is closed under composition, so is also this quantitative strengthening. When f has modulus mu and g have modulus nu, then the composition first f then g has modulus the composition first nu then mu. And observe that here the roads are the orders are changed. So we first apply f and then g, but we first apply the modulus of continuity of g and then the modulus of continuity of f. And classical notions of quantitative continuity can be recovered in terms of characterized in terms of modulus. So for instance, Lipschitz continuity, which you may be aware of, Lipschitz continuity in a bounded space are precisely those functions that has a modulus of continuity which is bounded by the identity and some additive constant. This is not necessarily the Lipschitz constant itself. This is more subtle, but still they have this characterization. And beyond Lipschitz continuity, there's Hölder continuity, and this is characterized by functions having a linear modulus of continuity. So here, the constant appears as factor in the Landau asymptotic big O notation. And here you see an example of a function which has a very large modulus of continuity. This is a function 1 divided by natural logarithm of e divided by x. Observe that this function on argument x equals 1 has the value 1. And on argument x equals 0, this superficially may seem to have a singularity. But if you look more closely, heuristically, e divided by 0, that's infinity. The logarithm of infinity is infinity. 1 divided by infinity is 0. And indeed, one can easily see that this function does admit a continuous extension towards 2, 0, including 0. It maps the unit interval back to the unit interval, and therefore is uniformly continuous, has a modulus of continuity. More precisely, it has an exponential modulus of continuity, asymptotically growing, mu of n growing exponentially, but no sub-exponential modulus of continuity, reflecting and capturing that this function is very steep here towards 0, much steeper than, for instance, the square root function, which, as you recall, is Hölder continuous and therefore has a linear modulus. So, put differently, this function is very sensitive in the sense that in order to approximate the value, the output up to error 2 to the minus n, one needs to kind of know the argument x up to error 2 to the minus 2 to the n, so exponentially more precise than the value. And one can push that game further by iterating h. So the composition of h with itself is again mapped from the unit interval to itself. And one can see that this even has a doubly exponential modulus. So it's even more steep. And of course, there's no stopping here. We can consider triple composition, quadruple composition, and make the modulus of continuity climb up a hierarchy, a tower of exponentials. So these are all continuous functions, but they are with increasingly worse quantitative continuity properties. And these properties are important for our later investigations of the main theorem, quantitative refinements of the main theorem. But first, let us recall classical spaces where a Turing machine can operate on without requiring any encoding. Right, before I forget, sometimes I will require this continuity notion only to hold for all sufficiently large n. Qualitatively, this of course makes no difference, but quantitatively there's sometimes a benefit in this. Okay, so let's talk about basic spaces. Basic spaces are the spaces where Turing machines can already operate on kind of natively and therefore don't require any coding quests or issues. And the computing properties on such basic spaces, this will be our guide when we try to generalize it to other spaces. That should include the basic spaces, of course. So the classical Turing machine that you are well aware and familiar with is one which operates on inputs of being finite binary sequences, let's say, and output also finite binary sequence. In general, this is a partial function because in some inputs, the Turing machine may fail to terminate and therefore have undefined value. Now, these finite binary strings are suitable for encoding discrete spaces, right? Because they're countable. But as soon as we want to discuss computing and even complexity over spaces of continuum cardinality, such as the real numbers, continuous functions, etc. There we cannot even encode them over finite binary strings. So that's what led to the so-called type 2 machine. The type 2 machine receives as input an infinite binary sequence that is an element of Cantor space written on its, let's say, input tape. So that just happens to be on the tape once the machine is turned on, and then it starts operating and starts producing bits on its output. And in the end, there must be an element of Cantor space in the output tape that is an infinite binary string. And of course, this cannot be achieved in finite time. So such a type 2 machine must necessarily compute unboundedly long. And there's a subtle requirement that it must not revert any output symbol it has ever written. Otherwise, there will be confusion about which symbol is final and which one is not. So that's a type 2 machine. And this is the one that has been used heavily in computability investigations by the Weyrauch school. But there's also the Oracle machine model, where remember that the Oracle machines have been investigated by Alan Turing in his PhD thesis. An Oracle machine has an oracle that is a set of finite binary strings fixed and attached to it, and it has a special dedicated oracle tape on which it can write a finite binary string and then can enter a query state, and the next step, in one step after the query state, it will have received the answer of whether the finite string on the query tape is an element of the oracle, the set of finite binary strings, or not. That is, it has received a 1-bit answer to a possibly undecidable problem. And by replacing the one oracle with a different one, one can consider oracles as arguments, right? So attaching a different oracle will lead to a different behavior of the machine, and therefore this is a kind of an argument to the machine, maybe an argument of this type. So this is, remember this notation, this is notation for the set of all functions from y to x. So this is the domain of finite binary strings, and the comma domain are just bits 0, 1, yes or no. And such an oracle machine thus receives access to an oracle, can make such queries. It also receives as argument on its regular tape, let's say a finite binary string, and it produces as output a bit 0, 1, so that means it answers a decision problem. And we will maybe consider currying this computation by oracle machines. Instead of having this mixed type of arguments, we will consider just oracle arguments and output being of same type. So kind of currying this part as here as argument in the exponent here. So in this sense, all three machine variations of the Turing model compute partial functions from a certain basic space back to the same basic space. And we don't need to define any way of coding when we consider this. Sometimes it may be beneficial to consider the natural number replaced by the set of unary strings. We call our difference between unary and binary encoding. And we may also sometimes consider even higher type oracles. So if you see the hierarchy from here to here, climbing one step further, this exponential hierarchy leads to this, what I'd like to call hyperspace. Okay, that's a space of mappings from total oracles to 0, 1. Right? So that's a total oracle to 0, 1. And hypermachine, which I'm not going to define here, but instead refer to Florian's and Akotishio in my 2016 LIX paper. That's something that transforms such hyperoracles to hyperoracles. When we equip these spaces with the following metric. This is the metric of Cantor Baire space, right? I keep calling this Baire space, although this is actually not Baire space because this is a compact space when equipped with this metric, and this will be relevant soon. So, so now we have a metric on these spaces, and we can start to talk about connections between computability and complexity and topological and metric properties of functions and computations. And that's exactly what we do now here. We record three main properties of computing on basic spaces, and then we will proceed and try to generalize this to spaces with encodings over basic spaces. And the first such property is the benefit of compactness. Namely, if we have a total computation that has domain a compact subset of such a basic space, that is a closed subset, then there exists a time bound. Then there exists a function t, which only depends on the number of the bit to be output. It only depends on the output, but not on the input. That's the important and subtle point that I'd like to stress here. In the discrete setting, right, we usually use n to denote the binary length of the input, and then measure computational cost in dependence on this length of the input. And this exists because, well, for every possible input string in the domain, the computation terminates after a finite number of steps, and taking the maximum over these finitely many finite numbers is again a finite number that's a bound that only on the computational cost and the time bound that depends only on n, the input size, but not on the actual value of the input itself. Here, there's infinitely many, there's uncountably many possible inputs. Recall that every real number has uncountably many codes in the case of dyadic and in the case of sign-digit encoding. So even if every single of these cases has a finite number of steps until it produces a certain nth output bit, then it's still not at all clear and in general actually wrong that there's a bound on the this number of steps that does not depend on the actual value of the input. We cannot just take the maximum over these uncountably many, but here compactness comes to the rescue. When the domain is compact, then by compactness and continuity consideration, such a finite time bound exists. And that's what we want for complexity theory, and that's what we therefore also want to have for spaces equipped with the encoding general spaces. The second property is that, which is sometimes called the main theorem, but here it's kind of trivial because we're talking about basic spaces without encoding, namely the observation that any computable functions on these spaces must necessarily be continuous. That's easy to see, so I will not go into this detail further, but proceed to the next property, namely a quantitative strengthening of this main theorem. Whenever a function is computable in time t of n, then it has a modulus t of n plus some constant. Or put differently, computational complexity bounds give rise to quantitative continuity bounds. Or put things the other way around, when a function has a large modulus only, like the ones with exponential or double exponential we saw on the previous slide, then it's no way that this function can be computed efficiently in polynomial time. Or put even more differently, if we have an algorithm that computes this function in exponential time, then this is already good. This is already optimal because the function may have an exponential modulus. Or put even more differently, we should compare the performance of an actual algorithm, not assess the performance not absolutely, but in comparison to a modulus of continuity. And this is exactly what the definition we want to propose here. Namely, we call a function computable in a relative polynomial time if it is computable in time bounded polynomially by the output parameter as usually, but also bounded polynomially by the modulus of continuity, or more precisely by least modulus of continuity. So this is kind of like a treatment of NP-complete problems, right? So when we have an NP-complete problems, we don't even expect the polynomial time solution anymore. But if we have a algorithm that runs in exponential time, then we know that this is good enough for an NP-complete problem. And sometimes algorithms even, so the goal is sometimes to improve algorithms from doubly exponential to similar exponential running time. And similarly here, when a function has a large modulus of continuity only, then we should assess the performance of an actual algorithm relative and in comparison to this modulus of continuity. This is a topic that will turn up frequently again later in this talk when we discuss also other information theoretic low bounds to computing on continuous spaces. So that's wraps up about computation on basic spaces. Now we should talk a little bit about why we want to consider basic space beyond Cantor space. This is what my school has been focusing on for many years. Why would we want to consider this bare space? I keep calling it bare space, although it's compact, as you know. And why would you even want to consider this hyperspace? Bare space has been considered by Akitoshi Kawamura, for instance, in his PhD thesis. And the reason is becomes apparent when we start to discuss function spaces over these basic spaces. So let's recall the Cantor space of infinite binary sequence, and let's consider function from Cantor space to Cantor space bound total function, which is 1 Lipschitz. So the distance of the values should be at most the distance of the arguments, both elements of Cantor space, equipped with this aforementioned metric. And one way of looking at such a function is to regard it as an infinite complete binary tree whose nodes are labeled with bits. And we say that again. If we have such a function, then the 1 Lipschitz condition means whenever we provide an additional bit of, whenever we have an infinite binary string as input, but we keep looking at initial segments that grow 1 more bit added at a time, then this also means that we can also obtain 1 more output bit at a time. So there's a kind of synchronous process of improving the precision, and every single new bit that is obtained can be written in the corresponding node. So here, if we know the input only starts with 0, then there's only 1 bit output we may be aware of. If we know that the next input bit is 1, then that means another output bit is recovered, and so on. So a sequence of bits, and we can rewrite these bits into these nodes, and thus obtain a complete description of that function. It represents the function uniquely, and vice versa, so that we can identify such 1 Lipschitz function from Cantor space to Cantor space with a complete binary tray with loads labeled 0, 1, and vice versa. Any such labeled complete binary tree gives rise to a 1 Lipschitz function from Cantor space. So we can consider, that's the next thing. Any such unlabeled infinite binary tree can in turn be identified with the element of this bare space. How does that work? Right, remember this bare space means input is a finite binary string, output is a bit, and that's the same here, right? So input is a finite binary string, let's say 1, 0, 1, finite binary string, and output is the bit that is written into this node, so that's 1 bit. And so that's exactly what we have here. Every such complete binary labeled binary tree gives rise to an element of bare space, and vice versa. Whenever we have an element of bare space, we can write that into this nodes, right? For every finite binary string that corresponds to a finite path to some node, and then we write the bit value of this bare space element into this node, and thus we can actually identify. We can say that only one Lipschitz function from Cantor space to Cantor space is an element of bare space, and the set of all such one Lipschitz functions, which we're going to denote by a Cantor space prime. It's kind of like a topological dual, if you like. We can identify that. We can say this is equal to the bare space. So, and that's the reason why we consider this bare space, because it naturally arises as a space of functions from Lipschitz to Lipschitz function, namely the one Lipschitz function. And this benefit is that when we consider the application operator, so given such a function and given an argument to that function, an element of Cantor space, output the value of that function at this argument, another element of Cantor space. This this application functional, right? So it's mixed of higher type. Input is a function argument. This is actually polynomial time computable when considered C prime to be given by oracle access. So whenever the function under the key equation is kind of presented as an oracle, then we can evaluate that function polynomial time as follows. So input is a finite initial segment to the argument, and we're supposed to output a corresponding bit of the value, and we simply query the oracle for the value of the function for that bit, then output that bit. So using the bare space with oracle access to a Turing machine, that makes the application functional on this space C prime polynomial time computable. But when we try the same way of a Cantor space, which is actually common in computability theory, that's where we can do that. We can also encode this infinite labeled binary string as an element of Cantor space, enumerate the bit in this node, the bit in this node, and so on, enumerate all the bits in the nodes in breadth first search. That's an element of Cantor space, and vice versa. So we can actually also identify this space C prime with Cantor space itself. That's why people in computability theory love this, right? There's no need to consider higher type computation. However, from the complexity perspective, this is terrible, because now if we want to know, let's say, the value on this node, then we first have to skip. Remember, skipping tape cells in the Turing machine in Cantor space, this bit, 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 until we've arrived at the node whose contents, whose bit label we're actually interested in. And there are exponentially many of these, right? So that when we consider the function from C prime encoded over C, then suddenly the application functional is not polynomial time computable, whereas when we consider it as encoded over the bare space with oracle access, then it becomes polynomial time computable. That's the reason for considering this strange bare space. And of course, we can play that game further. What about the space of one Lipschitz function from bare space to bare space, which we might then call B prime? This is kind of can be identified with the space, this hyperspace, and so a hyper machine can compute that in polynomial time, but an ordinary oracle machine cannot. So this it kind of suggests and justifies the use of this higher basic space, and of course there's an entire hierarchy going on here that we may want to consider. So now we've discussed basic spaces and their computation and the three properties, the three main properties of computing over base space, as well as justified why we may need to consider various, actually an entire type hierarchy of base spaces of higher and higher types, right? Functions, functions on functions, and so on. And now when we have a more general or an abstract space, in order to define and study computation, we need to encode its element over one of the base spaces. So this is basically the Weyrauch theory of encodings. And right, so nämlich Weyrauch and Kreitz formalized encoding in terms of what they call a representation. A representation of a space X is a partial surjective mapping from a subset of Cantor space, in their case, Kawamura also considered bare space. So partial surjective mapping from a subset of a basic space onto the space X. So we want this to be surjective, to be onto, in order to make sure that element of the space X has at least one code, has a name. We don't require the name to be unique. That was not the case already in the real setting, as you may recall, far from non-unique. And we don't require every single code, every single infinite binary sequence in Cantor space. We don't require that every of them to be a code. That's why it's called partial mapping, and we use this symbol in order to indicate partial mappings. So this is a Weyrauch conception of a representation, of a encoding of a space. And when we want to discuss computation of functions between spaces, then that is defined in terms of transformations of codes of the elements. More precisely, let's consider two spaces X and Y and representation xi of X and representation upsilon of Y, and function from X to Y. So that's kind of the abstract space. And we say that a realizer is any transformation on basic spaces, on the basic space that translates names of arguments X into names of values f of X. Put differently, it's a mapping from the domain of the representation xi to the domain of the representation upsilon, such that the following property holds, where this symbol now denotes restriction. I will say something about that in just a minute. So to illustrate this complicated and abstract definition, here's a picture that shows it graphically, namely in terms of a commutativity diagram. So here we have our abstract function between abstract spaces, and we have representations that amount to codes of the elements of these spaces. And here's the translation of codes, so that whenever we take a code and the element it represents and transform it by the abstract function, that should give the same result as if we first translate it on the basic space and then consider the element it represents. And restriction here means we don't require this to be really equal. It is perfectly acceptable if this realizer calculates, operates on, has a larger domain. So that corresponds to Weyrauch. Otherwise, Weyrauch would call that strong computability, but this does not have nice closure properties. Instead, it's acceptable for this realizer f to return some possibly nonsensical value when challenged outside of the domain of the left-hand side. And computing a function now means to compute a realizer, and we already know what it means to compute a realizer, because that's a transformation on basic spaces, which we have discussed extensively previously. Okay, so this is a Weyrauch conception of a representation an encoding over Cantor space of infinite binary sequence. Kawamura and Cook have considered a different conception of representation, namely over the Baire space. Well, that's not technically true, but you may forgive me for this oversimplification of their work. And the reason, or one of the reasons is, of course, we already know that function spaces cannot be encoded over Cantor space unless they incur an exponential growth in cost, right? So that's one reason, and we'll going to consider different perspective on the same reason later towards in this early second part of this tutorial. So that's a Kawamura and Cook conception, and Andre Bauer, Lars Birkedal, and Dana Scott have considered even a further actually class, a category of spaces as domains for representation. So it's Cantor space. Here it's what I call, incorrectly called Baire space, and they call considered equilogical spaces. I'm not going to develop that further, but let me just mention that point out that many different ground spaces have been thus used for representations. The class of equilogical spaces in the end emerged as the as the most appropriate one because it has these nice closure properties. It's most appropriate for computability investigations, but we are interested in complexity investigations. So that raises the question, what is the right category of spaces here in this complexity sense? And second question is, which kind of representations are we interested in? Recall that already in the real setting, there are 4 different natural choices with highly different consequences on computability and complexity. So important criterion for representation to be computability theoretically reasonable. That's the admissibility as identified by Kreitz and Weierauch. So there, so here's for you to remind you that the 4 representations we've discussed informally briefly, binary, rational, dyadic, and signed digit representation, are indeed all representations of the form considered by Weierauch, namely partial surjective mappings from a subset of Cantor space onto the real unit interval. And let's call the first representation beta. So formally beta takes as argument an infinite binary sequence. One maybe one that does not start with 1, and then takes the value of this weighted sum. And since it's partial, we can make sure that it only attains, or that it attains precisely all values between 0 and 1 and not beyond. Similarly, for the rational representation, it's numerators and denominators alternatingly encoded in binary, and then all these binary codes concatenated, or conversely, given an infinite binary string, decompose it into these binary blocks, and then recover the numerators and denominators whose limit up to error bound 2 to the minus n, and then the real number under consideration. Dyadic representation, similarly, infinite sequence of binary encodings of numerators to dyadic rationals, and signed digit representation. Similarly, here we have 3 bits that we can re-encode as tuples of bits, right? So let's say 0, 0, 0, 1, and this as 1, 0. So this is again a partial map from Cantor space onto the real unit interval. And we already know that the binary representation is not suitable, but we want to find a abstract criterion for when a representation is or is not suitable for computability. And this is exactly admissibility according to Kreitz and Weierauch. So they call a representation admissible if it is first condition, it must be continuous. There are 2 conditions, and the first condition is continuity. That's reasonable, taking into account that any computable function on basic space already must be computable. So we want to keep closer until composition according to the commutativity diagram. And the second condition says that the representation must, in a sense, be maximal, must be universal among all continuous representations, among all that satisfy criterion 1. Namely, if any other continuous representation zeta must admit a continuous reduction to xi. So this symbol is to mean continuous reduction and is defined as follows. So between two representations of x, we say that zeta reduces continuously to xi if and only if zeta is a restriction, not necessarily proper, but restriction of the composition of xi with f for a continuous function from the domain of zeta to the domain of xi. So imagine f to mean translating codes of zeta into codes of xi, so that any continuous representation must admit a continuous translation of codes, its codes, to the codes of the representation under consideration. Or put differently, the representation should be maximal with respect to this continuous reduction among all continuous representation. So this is kind of a universality definition, maybe a little bit similar to NP completeness, which also means condition 1, the problem must be in NP, and condition 2, any problem in NP must be polynomial time reducible to the problem. So this is kind of one way of looking at this admittedly abstract definition, but the benefit of this notion is that any representation that satisfies this condition makes the main theorem one of the three properties of computation on basic spaces extend to represented spaces, namely that's the famous Kreis-Weyrauch theorem for admissible representation of xi and of x and y. A function from x to y is continuous if and only if it has a continuous realizer. So admissible representations are precisely those that translate qualitative continuity into the continuity of the realizers. That's a benefit, that's an advantage of having an admissible representation. And indeed, now it turns out that the binary representation is continuous, but it is not admissible. It violates the second condition of Kreis and Weyrauch, whereas the other three representations are admissible and therefore suitable for computability investigation. The first is not. Right. Now that having recalled that, remember that our goal is to devise a complexity or theoretical refinement of admissibility and of the main theorem. And indeed, we have such a refinement, at least for the real case. One part has been known and the other is new and a first contribution of us. So this, we're now making the first transition from qualitative to quantitative, from computability to complexity investigations. And it seems natural for this step to replace all the qualitative notions in the Kreis-Weyrauch theory, that is the continuity notions with quantitative continuity notions. So what we aim for is a kind of a rule that excludes not only the binary representation, where, for instance, addition, although Lipschitz continuous does not have a continuous realizer, is uncomputable. Addition is computable, it has a continuous realizer with respect to rational representation, because that's admissible. But what we do get actually, we can prove that a dyadic representation actually admits a polynomial time computable realizer of addition, and the sign digit representation even a linear time computable realizer, as you recall. And now we want to replace all these quantitative notions and qualitative notions of continuity in the Kreitz-Weyrauch theory, in the definition of reduction, in the definition of admissibility, in the hypothesis and the conclusion of the main theorem. We want to replace that with quantitative strengthenings. So what we're aiming for is a quantitative version of the main theorem, and actually we are happy to present here two such quantitative versions, at least for the real case. One pertaining to the dyadic representation, which has been kind of hidden but maybe arguably known, and one tightened one for the sign digit representation, which arguably is new. So the first says a function on the real unit interval has a polynomial modulus of continuity if and only if it has a dyadic realizer with polynomial modulus of continuity. So that here indeed qualitative continuity in the hypothesis and in the conclusion is strengthened to polynomial modulus of continuity in the hypothesis and in the conclusion, subject to the realizer with respect to the dyadic representation, not with respect to the rational. And if we consider even the sign digit representation instead of the dyadic representation, then one obtains this even more tightened connection. Linear modulus of continuity of the function corresponds to linear modulus of continuity of a realizer. So this is the kind of spirit of the results, the spirit of the results we're looking for, that we want to now extend from the real case to the general, to the more abstract case. So to summarize, part one of the tutorial, we've talked about computing on basic spaces, Cantor space, Baire space, and this kind of hyperspace. We've discussed some main properties of computation on these spaces. First property is that whenever the domain is compact, then we can get away with a single cost parameter that does not depend on the input, but only on counts the worst case number of steps until the nth output approximation has been produced. Quantitative continuity here corresponds to computational bit cost, so that led us to introduce this relative notion of polynomial time computability, which says it's only fair to to give functions more time to compute when they have a large modulus of continuity. And finally, we've moved on to recall the coding theory of other spaces, representations and realizers over Cantor space according to the Weyrauch theory, over Baire space according to the Kawamura-Cook theory. We've recalled their classical qualitative notion of admissibility and the main theorem connecting continuity of function to continuity of a realizer, and their strengthenings in the real case tailored to the real case, namely binary representation is not admissible. Here continuity of a function is not related to continuity of a realizer. Rational representation is admissible, which implies, according to main theorem, that qualitative continuity of a function is related to continuity of a realizer qualitatively. The dyadic representation is admissible, but it has a even stronger property, which we will capture formally in the second part, but here we just informally call it polynomial admissibility, namely here polynomial modulus of continuity of a function is related to polynomial modulus of continuity of a realizer. And the new result for the signed digit representation, this is even linearly inadmissible in a sense to be made formal in the second part, in that function modulus of continuity of a function is linearly related to modulus of continuity of a realizer. So that's our summary of the first part. And in the second part, we want to address the following question. That's kind of our cliffhanger. And then we want to generalize all these considerations. We want to generalize admissibility and quantitative. We want to define quantitative admissibility for more general spaces beyond the unit interval. We want to obtain a quantitative main theorem relating quantitative continuity of a function, quantitative continuity of a realizer for more general spaces, and we want to define relative polynomial time computability for functions between such more general spaces. And the more general spaces we're interested in is, for one, compact subsets of Hilbert space L2, but more generally higher type computation. And here's an interesting hierarchy of higher type spaces. So let's say we start with x being the real unit interval and consider this, that's type 1, right? That's real numbers. And we consider the space of one Lipschitz functions from the real unit interval to the real unit interval. We denote that with x prime or 0, 1 prime, and observe that this space, when equipped with a supremum norm, is again a compact metric space, according to Arzela-Ascoli. So we can apply the same construction again and obtain x double prime. It's a space of function nulls. And again, this is compact when equipped with this supremum metric. So we can do the same again, obtain x triple prime, which is a even higher space of even higher functions. So we obtain an entire and proper hierarchy of spaces of, in a sense, strictly increasing complexity. We'll make that more precise later. And we want to define what it means to be polynomial time computation on this hierarchy of spaces. Remember, that's a big open problem in computation complexity theory, defining complexity of such higher types. And that's what we're going to achieve in the second part. So to summarize, we will want to find complex criteria for complexity theoretically reasonable encodings of such spaces. We want to quantitatively refine the notion of qualitative admissibility of Kreis-Weyrauch. We want to obtain a quantitative main theorem beyond the real unit interval, and we want to define a relative polynomial time computation on such spaces. And we want to answer the question, which basic spaces are suitable? When should we use Cantor space? When should we use Baire space? When should we use the hyperspace? Or when should we use another space for encoding? And how does that depend on the space which we want to encode? So this is these are all for the part 1. And I'd like to thank you for your attention, and I'm now here and available in order to answer questions and to discuss things. Thank you very much.